talk a little bit about kinetic energy now. So we've already said that kinetic energy is the energy due to motion. The formula for kinetic energy is 1/2 the mass times velocity squared. So your mass is going to be in kilograms, velocity is going to be meters per second, and that's going to give us kilograms times meters squared over second squared, which is a joule. So once again, kinetic energy is not a vector. Even though you might be traveling at positive 3 meters per second squared, when you multiply these two vectors, you're going to end up with a scalar quantity. So the work that you do throwing something is going to give it a certain amount of kinetic energy. So let's take just a simple example. Let's say that we have a bullet and it's traveling at 200 meters per second. Well, the first thing we need to realize is that the mass of the bullet is 5 grams, and we're going to need to change that to kilograms. A gram is 1/1000th of a kilogram, so this would be 5 thousandths of a kilogram, which would be 0.005 kilograms. And it's traveling at 200 meters per second. So if I plug this into the formula, I get 1/2 of 0.005 kilograms times 200 squared. It's going to give us 1,000 joules of kinetic energy. Note that K is directly related to V squared. So if I double my velocity, my K will be 4 times as big. So if I double my velocity to 400 meters per second, I'll have 400 joules of energy. If I triple my velocity, it'll be 9 times bigger. And if I cut my velocity in half, then my K will be 1/4 as much. So I have to square that. So I would only have 25 joules of energy if this bullet was traveling at 100 meters per second. In order to change the bullet's kinetic energy, we have to do work on it. So if you wanted to stop the bullet, you would have to apply a stopping force in the opposite directions of its motion over a distance to do that. This is called the work energy theorem. So what that says is that the work that you do on the object is equal to the change in kinetic energy. Remember that any change is always the final value minus the initial value. So if we plug in our formula, work would be the force times the distance that we're applying it equals the final kinetic energy, 1/2 mvf squared minus 1/2 mvi squared. So if the bullet accelerated over a displacement of 0.4 meters, we could figure out how much force was exerted on it, right? We know that if it accelerates, so let's just draw a picture of what's going on here. We've got this is a rifle, obviously. This is 0.4 meters or 40 centimeters. And we're going to apply a force to it. And it's going to start with no initial speed. And it's going to leave at 200 meters per second. And it was a 5 kilogram bullet in the previous problem, so we'll just imagine it's the same thing. We already know that it starts with no initial kinetic energy because it wasn't moving. We know that if we plug in 1/2 of 0.005 times 200 meters per second squared, we get 100 joules. And that is going to be equal to the work done on it, which is F times D. So if we plug in 100 joules equals F times 0.4 meters, we would find that we had to apply an average force of 250 newtons to it. So that wouldn't be us doing it, right? It would be the expanding gas propelling that. So that would be the average force that expanding gas would exert on the bullet. Now I want you to notice that this is similar to some of the problems we did in kinematics, right? When we did this and we wanted to figure out how much force, we would first have to find the acceleration, and then we would have to equals F equals ma to find the force. So using this idea that the work done on it is equal to its change in kinetic energy actually simplifies our kinematics problems for us, because we don't have to find the acceleration anymore. We can use this idea that work is equal to change in kinetic energy, and it becomes a one-step problem. Versus before, where we had to go, okay, VI is 0, VF is 200 meters per second, X is 0.4, and now I have to pick a kinematics equation to find A, and then I have to multiply it by 0.005 to find F. So this is actually a great way to solve a lot of those kinematic problems when we don't know what the acceleration is, instead of using a kinematics equation and F equals ma. Also, if we have the force and the displacement at an angle to each other, we can still use this relationship. So let's say we're pushing that mower before, and we're going to apply 200 newtons at an angle of 30 degrees to move it 4 meters. And we want to know how fast it'll be going. Well, we know that the work done on it is going to be 200 meters newtons, times 4 meters, times the cosine of 30. And that's going to cause it to have an initial kinetic energy of 0 starting from rest, and then it will have some kind of final kinetic energy. So that work, 200 times 4 times cosine of 30, is equal to that change in kinetic energy, which is just 1/2 F squared minus 0, right? Because it started with 0 kinetic energy. So if I plug in for M, and let's just say that the mower, I didn't tell you what the mass of the mower is, so let's just say the mass of the mower is 100 kilograms. So if I plug that in, it equals 1/2 of 100 kilograms times VF squared. And this is going to be equal to 200 times 4, which is 800, times the cosine of 30, which is 5.4. That does not make sense. Let me try that again. Cosine of 30 times 800 is 0.0693 joules. I'm going to multiply that by 2 and divide it by 100. And that's going to give me a VF squared of 13.9. And now I'm going to take the square root of that. Which is going to give me 3.72 meters per second. So it will have a speed of 3.7 meters per second when it leaves at the end of that 4 meters. So that is your lawnmower. It's moving at 3.7 meters per second. All right. That's it for work and energy and kinetic energy.